Hello, my name is Sripathi, and the title of my presentation today is Helicality, an Isomap-based measure of octave equivalence in audio data. Octave equivalence refers to the perceived consonants of any pairs of tones whose frequency ratio is a power of 2. It is a foundational aspect of music theory systems, and concepts such as Thai in Carnatic classical music and tonets in German classical music rely on it. ISMIR systems use octave equivalence-based representations including chromograms and the more recent spiral scattering transform. They are also used as domain knowledge in deep learning systems such as harmonic CQT and harmonic filters. However, the discovery of octave equivalence from audio data has received less attention with the exception of these studies. In these systems, a representation of the time frequency atoms is provided, but interpretation is left to visual inspection, which is not scalable. Specifically, we build on the latter, where frequency subbands in audio data are embedded in a Euclidean space. Given an unlabeled audio dataset with n audio files, we compute a constant Q representation with 24 bins per octave. We restrict the frequency representation to 3 octaves of greatest variance and the time representation to a single frame of maximum energy. This results in a matrix of 72 rows and n columns. We extract Pearson correlations across all pairs of features and convert them into pseudo-Euclidean distances. Using scikit-learn, we compute a k nearest neighbor graph with 3 neighbors. We then apply multidimensional scaling to generate an embedding in 3 dimensions where the Euclidean distances are inversely proportional to the strength of the Pearson correlations. Each point seen here is a frequency subband, where the hue denotes pitch class irrespective of octave. The question we address is this: can we quantify the notion of octave equivalence in an audio dataset? To this end, we fit a helix to the 3D point cloud in an isomap embedding of frequency subbands. We consider the first 2 eigenvectors, which is the embedding in 2 dimensions. Then we compute the chroma centroids by averaging across octaves. Our postulate is that in an audio dataset with octave equivalence, these chroma centroids should form a circle. We extract a convex hull using the quick hull algorithm, denoted by the black line with squares. Its barycenter C provides the initial estimate for the circle center, denoted by the green square. Then we minimize a least squares objective using a custom Frank-Wolfe gradient. This objective is inspired by a least squares circle fit algorithm by Coop. Running through several iterations provides the final circle center estimate, denoted by the red diamond. On the 3rd dimension, we use linear regression to estimate a line fit. Using the circle and line estimates, we project embedding points on the helix in 3 dimensions. Then we define helicality as the Euclidean distance between embedding points and the projected points. We run numerical experiments on 3 datasets. For music, we examine the Tiny Sol dataset, which consists of isolated musical notes played by 14 different instruments. For speech, we use the North Texas vowel dataset, which consists of 12 voiced vowels by 50 speakers. For drums, we use ENST drums, from which we take a subset of isolated drum hits by 3 drummers. Here we have the results from the 3 datasets: music, speech, and drums isomap embeddings with the associated circle fit procedure. Music has a more helical embedding than speech and drums. Accordingly, music has a higher helicality score of 0.54 rather, followed by speech and drums. The initial results are in line with domain knowledge about these audio data types. Further, we examine the instrument classes in the Tiny Sol dataset. We find that horn has the most helical embedding topology, followed by accordion. Surprisingly, trumpet has a low helicality, despite the typical harmonic structure of its spectra. This bar plot illustrates the distribution of helicality scores in various instrument classes from the dataset. In conclusion, we have presented an algorithm to fit a helix to an isomap embedding point cloud and applied it to music, speech, and drum datasets. Future work needs to explore how well it aligns with human perception. Thank you.